I've started a recording.
Okay, so I need, I don't see anyone raising questions, so I need help with that. I only have my screen in front of me right now. Okay, so today is about a simple pump example in DEXPI. Actually, it's a PNID of a pump, and then we have a look at. I will show you how this looks like in DEXPI. Later, Judith will take over and explain how such a model could be represented in STEP. And then after that, I will discuss how we would do that according to IDO. Now, maybe a little disclaimer in the beginning. What we're not doing is to present a fleshed out and finalized recipe for converting PNID diagrams into different standardized forms. So we are really discussing sort of the fundamentals, basic considerations that need to be taken into account. So if you spot some issues and mistakes, that may as well be. We are abstracting away also a little bit, and you will find there are quite some differences between DEXPI, STEP, and an OWL representation according to IDO. Also because these different models are made for different purposes. So we have to keep that in mind. Okay, so last week or this week, we met with Plants and Bytes with Manfred Theisen and Markus Sömers. And they talked with us about the simple PNID of a pump, and they supplied us with some data, and this is what we're working with. This is our starting point. So you can go to their website and browse through their services. And in particular, they gave us a couple of files. So one is, this is also a file you will find on the DEXPI side. This is the DEXPI information model version 1.31. This is an XMI file. It looks like this. So it is not something you want to read manually. This is like, yeah, a bit shy of 9,000 lines. That's quite an effort to walk through. In addition, they supplied us with a little PNID. Now they have their own representation of DEXPI models in form of RDF. The established exchange format is Proteus for DEXPI, which I don't want to show you now. I don't want to get into it. But they also have a translation of DEXPI models into RDF, and this looks a bit like that. And even let me show you the model first, and then let's go back to that later. So here we have a picture of the model. Extremely simple. So a model would involve a root node, something to start with, and that would be a DEXPI model. The DEXPI model then has a conceptual model, which then has a list of tagged plant items. And here we have a centrifugal pump with a number of properties. So a centrifugal pump can have a shaft power, volume flow rate that it is designed for, a description, and a tag name or tag number. So these would be the attributes related to the pump. I hear some noise. Could we just mute everyone, please? Okay, and then the pump consists of nozzles and a chamber that these nozzles are connected to. And in order to draw PNID diagrams, these nozzles are related to something they call piping nodes. These are connection points to know where to connect the piping to the symbol of the pump. Let me show you how this looks like. So on the Plants and Bytes website, you can find this little software. This is the PNB toolbox. And there you can load models and look at them. And this is the simple example that we are looking at. So this is a symbol for a pump with the two nozzles, and one and then two. On the left-hand side, you can see a breakdown structure of our model. And on the right, you see this graphical representation. And when we click on it, you can highlight it, and you can click on the different parts, and then they would be highlighted here on the left. So we can click on the nozzles, and we see this is nozzle 1 with some properties, and this is nozzle 2 with some properties. And this is the entire pump object with the chambers and the nozzle list. And now imagine this can be done with a complex PNID, and you can sort of zoom in, zoom out, browse around and click on things and see the properties listed. So for example, for our centrifugal pump, we have our design shaft power, which is just set to something that is called here null power, which is equivalent to this value is simply not given at this point. Then we have design volume flow rate. That seems to be sort of a complex property with a unit and a value. And the unit is cubic meter per hour. The value is 200. And then we have a description of the item. And we can sort of open this up here and see that it is a cooling stream pump. And this is provided in different languages. And the tag number is simply P123. Okay, so this is a viewer. And I will close these. And this is the underlying RDF file for that diagram. Diagram is a bit a stretch. It's just one symbol, essentially. And this includes the information for displaying the PNID. And Plants and Bytes also provided us with a stripped down version without this display information. So there's no layout information now in this file, and this is much more manageable. This is just a bit shy of 70 lines. So this is something you could analyze manually and understand everything about it. Okay, so with that in mind, I would now hand over to Judith to explain how this model, and that is this model, very simple, would be represented in terms of step. So over to you, Judith.
Okay, thank you very much. I'll just grab the screen. Can you see my screen?
Yeah, we can see it.
Okay. So what I'm going to do is show you what the information would look like just as a sort of instance model from the step the step starting point. So these step models are defined in SysML, and what I've done is I've just created an instance model. So I'm not going to show you an application for navigating it. It's literally a picture of the sort of things you can do. The step standards are exchanged usually using an XML. So there's an XSD format for these, and they're also exchanged with REST APIs. So there are parts of the step standards define what those are. But I'm just going to walk through that same example that we were just looking at earlier. So this is the original picture, and I'm going to walk through this piece down the bottom. I'm not going to go into much detail, but I'm just going to highlight some of the interesting features that the step standards have. Okay, so the first thing I'm going to do is talk through the pump itself. So these three boxes here are the pump. So what step does on all the sort of entities in the model, they have what we call a master version view. So everything, the parts and the breakdown elements and the system elements, etc., and the requirements and all those elements of the step standards have a master thing, and then that master thing contains all the versions, and the versions can have multiple views. So you could, for example, have a costing view of something and a manufacturing view, and the properties for those are contained in different pieces of the version. So on this diagram, I've just put a green box around the things that are like that. So here's my pump. And if I just scroll down here, here is a nozzle, and here is a chamber. So that's the equivalent of the nozzle here and the chamber here. So the next thing I want to highlight specifically on the STEP standards that's interesting is the relationship objects between things. So I've coloured them in blue. So these things here are all relationship type objects. So between the pump and the nozzle, I have got a relationship object, and that relationship object is classified as something. So at the moment, I have classified it as this breakdown element hierarchy, which is some external reference data. So this is where we start really getting interesting with the owls and owl classes and things. We've defined what this relationship is, which is a hierarchical relationship, and there's a definition in here in the ISO standard for 10303. The other interesting thing about these is you can start, or I'll come on to that a bit later, actually. What I've got down here, here's my nozzle. The other thing you can do with these is you can actually classify them as something in themselves. So here's my breakdown element view, which will have a master and a version as well. I just haven't drawn them for clarity. But it's been classified, in this case, it's been classified as a feed nozzle. And what I've done here is referenced the 15926 part 4 for a feed nozzle. So if you go on the ISO standards, you can find 15926 reference data, and it will explain what is meant by a feed nozzle. So that is referencing that section. So all these objects, whether they be relationships or nodes, they can all have a classification on them, or multiple classifications even on them. Okay. Just looking for, make sure there's no questions. Okay, so that's the sort of interesting one for relationships. The other one I've put over here to elaborate a bit more. If I come back to my picture, so this picture has a centrifugal pump with a property about the volume flow rate here. So again, in STEP, it's not just a property on the view. What we do is we actually have a property assignment relationship between the property, which is here, and the pump, which is here. So here's my property assignment object. I haven't classified this one, again, just for clarity, but what you can do on these relationships is you can add more information. And the STEP standards have lots of different things you can add to an assignment. I've just added a couple just for interest. So I've just said that it's got a date time assignment, which is a valid from. So basically I've said that this pump property, sorry, this pump has this property valid from the 10th of October 2024. The other one I've got here is the person who assigned that property. So I've got a assigned person organization. In this case, it's Pumps Limited. So the organization Pumps Limited has said that this property of the flow rate is valid for this view from this time. So that's the sort of things you can do, and there are many more. You can add assumptions, justifications, conditions, and all sorts of things actually on the relationship itself. So that's a key feature of the STEP standards. All these relationship objects have this sorts of information you can add to them. Just a little bit more on the property. So here's the property. It has a definition. Again, I haven't put much on that definition. I've just added the allowed units, and the allowed units is pointing to an external unit which has some reference data. So again, there is a reference data that defines what this unit is, and if you look at the details of that reference data, you can see, I've just copied it up here. You can see that it is it's a derived property definition, and it is in meters cubed per second. So it's using the SI units for those. This gets very interesting in that you can then generate more types of units. If you look at this one here, it's actually measured in meters cubed per hour. So with the step standards, you get the SI units and derived SI units, but you don't get the any other units. So you, as a user of the reference data, or for the domain you're in, you can generate your own units and effectively create more reference data that tells you what those units are. So you can easily create another one that says the definition of this is meters cubed per hour. Okay. Just a little bit over here. The other thing that's interesting about the step standards is you can have multiple or sets of information on things, as well as just individuals. So it's not just a single descriptor. For example, here you can have sets of descriptors. So I've got a descriptor set on this pump, and basically what they do is I've got a string which is the pump, a cooling stream pump that's in French, and I've got another string that is a cooling stream pump that's in UK English. So basically we have a definition of a language which has got a country code and a language code, and then what we do is we say, okay, I'm assigning this descriptor in the context of something. So I've got a context over here that says this pump, its description for Pumps Limited is this string, which is in UK English. And you can do that with identifiers and things and all sorts. So the pump can have multiple identifiers in different contexts as well. It's a very quick whistle-stop tour of this thing. I wanted to just show you. So I've literally just touched on a few small areas of STEP. If you want to see, if I just bring up this one, if you want to see the scope of STEP, there's a nice picture here on the ASD SSG website. I've literally just touched on something in product structure, I think, a tiny little piece in the middle of here, which I've touched. So that's a sort of pictorial view of the STEP standards. And if you actually go and look on the online browsing platform for STEP, and you look at the 10303 part 2, you can see all the definitions in here, and there are, I would say, thousands of these definitions. So there's all these sections. You can go and read what all the definitions are. So not only are there multiple sections like this, but they all have multiple subsections in them. So there's a lot of information that you can look at freely online. Any questions, or I'll hand over to the next agenda item.
I think we have one question. Yeah.
How
So
is maturity of the data related to the pump from conceptualization to installation at site further during maintenance captured? Okay. Okay. So if I just come back to this this picture, I've only touched on a small part here, but the scope of the STEP standards, the one I'm really talking about is AP 239, which is product lifecycle support, and that can cover the whole range of the lifecycle through these concept to disposal, if you like, as it shows up here. We haven't got the time in this session to show that, but effectively everything can be related through all these pieces can be related to each other. So you could have a design breakdown, and you can have an asset breakdown, and you could have a as-built breakdown, etc., all related to each other. And I'm not sure, so it's very difficult to capture in a few sentences, but that is the whole point of AP 239 or 10303 239 as the standard goes.
A new comment which simply said thank you.
I think there's one more question from Asma, and she asks, is there work to update this SysML1 model to SysML version 2?
I'm not sure. I'm not involved in the current editions of the models. So I'm more involved on the content of the models rather than how they are modeled. So I'm not sure what the current status is for V2, but V2 is as far as I'm aware, not fully out yet. So I'm sure it's in the pipeline. But I'm not sure of the status.
It has been discussed several times in the committee that is responsible for 10303, and for the time being, it has been decided that we want to wait a little while until the version 2 is more mature.
Okay, if there are no more questions, then we just move on. Share my screen again. All right. So now we're talking about this model, and we saw that what we see here graphically represented actually exists in form of data as an RDF file. So RDF stands for Resource Description Framework, and an RDF graph consists of a number of triples. And these triples can be represented in different ways. And here we see one way of representation, and this is called the turtle format. So it looks like this. And now let's go to how would we, let's talk about how would we go about taking this data and create an OWL ontology that is aligned with or complies with the industrial data ontology. So what is this data? So for that, let's just have a small detour. So an RDF document is essentially a document which we would classify as an information object in IDO. So if you see this prefix LIS, that just stands for Lifecycle Information System, and that is, for historical reasons, we use LIS as a namespace prefix or namespace abbreviation for these terms in IDO. So wherever you see LLS, that means this term is defined in IDO. So object is one of these top-level categories. Information object is one of those direct subcategories in IDO. There we can place this class document. All these yellow boxes here, these are classes. And in this representation, the purpley boxes, they represent individuals or instances of classes. Now, similar to UML, we have these arrows with the empty arrowhead. This just means subclass of. And the arrows with the full arrowhead, this just means without any label, means is a member of. So this RDF document is a member of this class document. And when there is a label, then this is the name of the relationship between these two individuals. So this RDF document may have a triple and another triple and so on. It may have lots of triples. And these are content parts. So we can describe an RDF document in form of a breakdown structure. And then looking at a particular triple, we can break this down further and can say this is the subject, this is the predicate, and this is the object, which are the three different parts of a triple. And that is all good and fine, but what do we do with that? How do we assign meaning to this in terms of IDO? And this is where we would need to map these information objects to things that carry that meaning, other resources in the RDF framework. Here I labeled this represents. We may also use the IDO relation is about, that would connect information objects to other things that the information object describes. And the relation is called is about. If we go to protege, we can find, so this is protege. I go to entities, object properties. I list all my object properties and I find this is about relation. And in order to figure out whether or not I can use it, I see here as a domain restriction, it has to start from an information object. So any information object may have an is about relation to something else that the information object is about or describes or represents. So that's just as a back up for what comes now. I would like to take this file, take these triples, and I would like to talk about them. I would like to represent them as an RDF document. For that, I use the following syntax. So the first line here is a triple subject predicate object, but I will use it in this notation. So the lower one, subject, and then there's an arrow that represents the predicate to the object. But that is not really a faithful representation of an RDF graph, so-called RDF graph, because the predicate here can be an object or a subject of another triple. So RDF graph should it lends itself to think about an RDF graph as a directed graph, but it actually is not. So there are, this can be become a little tricky. Doesn't play a role here now. That's why I use this notation, but as a directed graph. But just keep in mind, an RDF graph is not really a directed graph. So now I take all these triples and I just had some time and I put them all in a graph form. So now instead of having to look at this, I now have a more graphical representation. I like it better. I can think better in terms of a graphical representation. So we see that our root node is this example 1N1 node, which is categorized as a conceptual model. It is also categorized as this meta object. Then it has a tagged planter item in DEXPI, which is this example 2, N2 node in RDF. Remember, we are still in pure RDF. This has not yet an ontology. It has nothing to do with OWL at this point. This node N2 is a centrifugal pump. That pump has, or this node has a tag name P123. It has a design shaft power, which is not set. Therefore, it is it points to this null power RDF resource. Then it has chambers. This N3 node is the chamber, the only chamber that this pump has in this pump model. It is categorized as a chamber and as an object, and then it has, our pump has nozzles. So we see N4 and N6, they are nozzles. Those nozzles are related to the chamber. They are objects themselves. They have a stub tag name, N1 and N2 in this case. And they have piping nodes. This relates to the display. This is basically important for displaying PNID diagrams to know where the connecting line should really connect in the picture. So the piping node is important for layout. And then we have a description of our pump, which is yet another node, N9, and attached to that node we have our different descriptions in different languages. So we have cooling stream pump in English. I think this is that might be a Chinese representation, which doesn't render here, and then we have a French representation which is not set. So it's set. It's pointing to a null string. And then finally we have a quantity value. So we have a design volume flow rate property pointing to a node which says 200 cubic meter per hour. Okay, so that's it. That's our model. This is the same model we saw before in this little PNB toolbox application. And you find all these attributes here as well, just rendered in a different way. Okay, so now what do we do with that? A first step is to think about, this is to keep in mind that this is just RDF. We want to go into the OWL world. So similar to IDO, OWL also prescribes certain categories that we need to keep in mind, or that we need to categorize everything that we want to talk about in OWL into. So that means in particular, for every of these nodes or RDF resources, we need to think about in which OWL category do they fall. So are these classes? Are these individuals? Are these properties? If so, which kind of properties? Or are they literal values or data values? So I did that, and we arrive at this picture. So I just colored the nodes, and I say, okay, my DEXPI conceptual model is a class. My meta object is a class. So all these yellow boxes, these are classes. All the purple ones, these are individuals. And things that sit on arrows, these are properties. And there are two types of properties. In OWL, there are three, but we only use two here. The arrows between purple nodes, between named individuals in OWL, these are called object properties. And the arrows between the purple node and the sort of a white node, these are connecting data values to a named individual. And these are called data type properties. So now I colored everything in according to how I see it. There might be a mistake, but I think it looks pretty good for now. We could have a look. So the name or the tag number, that would simply be a string. The null power resource, we represent that with an individual. And the null string as well, which we find over here. The different strings, these are literal values. And then everything else falls into classes and individuals, and the other properties are simply object properties. Okay, so we have a colored picture, so we know for each node which OWL category applies. I think that's already quite helpful. Now we need to actually look at our, maybe a small detour. When we look at our DEXPI model or DEXPI meta model, we find words like meta object and conceptual model and centrifugal pump. And we find that there are individuals that are members of these classes. In the original RDF representation, two relationships have been used to say that, for example, this node N1, our root node for the entire PNID model, is a conceptual model and is a meta object. So there are two different relationships used, meta type and RDF type. So why is that? It turns out this is a particular decision that Plants and Bytes has made for a particular purpose. It serves a purpose internally, let's say. When going from our RDF representation into an OWL representation, I simply simplified that. I said, okay, these arrows are represented by RDF type only. And this is the way how OWL wants to have class membership represented. So that's one simplification. Then there's more that is important here. We are now connecting to the DEXPI meta model. And I looked at the, I'll just show you. I looked at the DEXPI information model version 1.3.1, and that's quite a large file. And I looked up these nodes: centrifugal pump, meta object, conceptual model, and so on for all the classes. And I tried to wrap my head around how this really works under the hood. And there we see there's a lot more going on. So I put little stars on the nodes that we are dealing with. So the centrifugal pump, for example, is categorized as a pump, and it lives side by side other types of pumps: the custom pump, the rotary pump, ejector pump, the reciprocating pump, and so on. The custom pump is a bit special. It's categorized as well as a custom object. Otherwise, everything is a pump, and every pump is equipment. Now, equipment can be associated with nozzles, drying chambers, motorized component, gearbox, and these are categorized as well as some high-level classes. So they're called in DEXPI custom, attribute owner, and conceptual object. So these in OWL, we would not distinguish between these two. Everything is a conceptual object and everything can have attributes in principle. And there's more going on above equipment. Equipment are things that can have nozzles, that are tagged plant items, and that can own or can have chambers. A tagged plant item has its own sort of model or superstructure, and the chamber. So this is not a subclass relationship. This is just saying a chamber owner can have chambers, and a chamber is something that is not actually categorized as equipment in DEXPI. It is just categorized as a conceptual object and a custom attribute owner. So it lives like on the top level, it seems. And the chamber can have a whole range of attributes. So you can describe it in terms of its function. You can set tag names. You can give material codes and some nominal diameter type representation. And you can associate to a concrete function. You can set its height, inside diameter, length, nominal diameter, width. You can set pressure properties and temperature properties. So there are a whole range of properties that you can associate with the chamber. This is all part of DEXPI, and I tried to draw it out as we would represent it in an ontology. So we need to keep that in mind. There's a lot more going on in DEXPI. But let's go back to our example, where all this is not contained. So we are only looking at this very contained mini PNID of a centrifugal pump, and we're just now ignoring this superstructure and all the properties that are associated, for example, with the chamber. Okay, so let's take this material here. Let's remove all the instance data, and let's see how we would categorize this information in terms of IDO. So in principle, all of that is data. And my first step would be to take all these DEXPI classes, all the DEXPI individuals, and say they are information objects. Intuitively, DEXPI provides us with a data model to represent P&IDs. And as a first step, they are data, and I categorize them as information objects. Now, these information objects, they talk about something else, something in the real world. And for that, I use these, which are now called both represents / is about. This is about is actually the one from IDO. And I connect, I didn't do this for all of them, but I connect them to things that I find and can categorize in terms of IDO. So let's look at, for example, our centrifugal pump. And let's follow this arrow here, and I know where it ends up. It ends up here. And I find a reference data item, centrifugal pump, in the PLM RDL. Now you can use any RDL you want. I chose to use this one. And let's have a look at the PLM RDL. I go for that to my to this page, the page hosted at PostCisa, where we can look up reference data from that was introduced in the Ready project. This is part of the PLM RDL. And here we have our centrifugal pump. It has an identifier within PCA, and that notion of centrifugal pump is then aligned with the DEXPI P&ID. Oh, this is just a symbol. It's aligned with the SHIFOS RDL of a centrifugal pump and with the PCA RDL of a centrifugal pump. That's why I used the PLM RDL as a reference data, because we get the alignment with SHIFOS and DEXPI. So we have our centrifugal pump. We have our chamber. This time I used the PCA RDL because I couldn't find it in the PLM RDL. And we have our nozzle. And I declare all of these to be physical objects. Now you may argue that's not really true. Well, let's have a look. For our centrifugal pump, we can see it's a pump as a superclass. The pump superclass is an artifact, which is an inanimate physical object, which is a physical object. So that is okay. For the nozzle, this works out the same way. For chamber, it doesn't, because it doesn't exist in the PLM RDL. However, I chose it anyway because, and you may disagree, in the reference data definition, it says it's a physical object. The chamber is a physical object. You may now argue, or let's say from the IDO point of view, you may argue a chamber is actually the space and not the physical object. It's the space that is contained by a physical object. So you may want to make this distinction. For this representation here, I treat it as a physical object. But we can talk another time about how this would be done when we treat it as a space or a location. Okay, our DEXPI piping node. This is the little node to pinpoint where things are connected in the DEXPI diagram. These become, in my book, a location. The unit, which is this individual here, the DEXPI volume flow rate unit dot meter cube per hour, that becomes also reference data, and I picked it again from the PLM RDL, where we have introduced unit of measure. Again, you may use a different RDL for your purposes, so you can look that up. Let's go back here. How was it called? Meter cubed per hour. We find it here, and this is the reference data item. We find it is written down in this way, and it is aligned with SHIFOS, QU, DT, and the PCA RDL. And we find some more information about it here in the ontology. And it is a unit of measure, and a unit of measure is an information object. And so on. We can do that for everything else, and basically have these information objects as they occur in the DEXPI model for describing PNIDs. We can align them with reference data or classes and individuals that are categorized according to IDO. This is how we can bridge these two notions. Now let's look at some instance data. I said before that I leave out the instance data. Let's put it back in. And this is really a simplified view. If you want to treat your chamber as a location, this would look differently. Right now, the chamber is just a physical object. So then I would say my centrifugal pump has these different parts. It has a nozzle, and it has a chamber. And then I categorize all these different nodes accordingly as physical objects in IDO. And I relate them with this has-part relationship from IDO. Or we may use actually a more specific relationship when we only talk about physical objects. And then what I haven't done here is now relate these different nodes, the nozzles and the chamber, because they are actually connected. So this is missing here. Now let's go on. We saw that our example of a centrifugal pump actually has a design volume flow rate of 200 cubic meter per hour. And this is how it's represented in DEXPI, now turned into an OWL ontology and sort of put underneath an information object. So we have a node N2, that is the centrifugal pump. It points to what is called in DEXPI design volume flow rate. This is the node N8. And then this node has attached to it the value 200 as the flow rate value, and this individual as the flow rate unit. Now in IDO, that's a little bit different. It's almost correct, but in IDO we make one additional distinction. Namely, we separate this quantity into an individual that carries the value and the unit, and an individual that only represents the quantity. And this is how it's done. So it's almost the same picture, where N2, our node N2, is a centrifugal pump, which is a physical object. It points to the quantity N8, the volume flow rate, which then points to an individual that is dedicated to representing data. And to that individual, we have associated the value 200 and the unit. So this individual that has the unit and the value, these are quality datums, which are information objects. The unit is a unit of measure, individual, which is an information object, and the 200 is simply a literal value. Now our DEXPI property, we can introduce or model as a shortcut relation. Now I skipped over how these things are called. So N2 is connected to the quantity N8 via this has physical quantity relationship provided by IDO. And this N8 node, which is the quantity, is related to the data, which is 200 cubic meter per hour, is missing here, via this quality quantified as relationship. Now again, this may sound a bit strange using these long names. They make a lot of sense, but they may take a while to get used to. But you can use them as an underpinning model for the DEXPI relationship, which is design volume flow rate. Now again, in DEXPI, the design volume flow rate points directly to the node that carries the unit and the value. And you can do that here as well by abbreviating these two steps and simply say design volume flow rate points directly to the data with the unit and the number, abbreviating has physical quantity and quality quantified as. So the quantity is sort of encoded in the relationship itself. So that's a way to do that. I think we are nearing the end, and I would like to stop here. You're very welcome to ask questions. We try to answer them now and If not, then we collect them and answer them next time. There's a lot more to talk about. You see, this is rather different from the STEP model. The STEP model is a lot richer and talks a lot more about how to work with this model over time, how to manage this information. Versioning is taken care of. Certain properties hold over a certain time period, and so on. There's a lot more that Judith was talking about, which I did not touch upon here. We should address this at some point, but right now I just focused on what I've presented. So taking the PNID model in form of RDF data, turning it into an ontology with some simplifying assumptions, categorizing it according to IDO. In my book, this is these are information objects, and they need to be related to description of the real world. And for that, I would use reference data. And IDO provides us with a way to connect these two categories, or the category of information objects with other categories in IDO. And then we need to take care of how we model quantity values. And here I introduced a distinction between the quantity and the data that carries the value and the unit. I think overall this is quite in line, but there are certainly some open points, some more questions, and this presentation here simplifies some things from the DEXPI point of view. And I must say I'm not an expert in DEXPI, but I hope I got it more or less right. And if not, then we will talk about it with Heiner, and he will set it right later. Okay, so I will stop here and invite for questions. We have 3 minutes.
We have 2 questions in the chat.
Okay, then I need to stop sharing because I can't read otherwise. Okay, so we have Mikkel asking, do the DEXPI properties like DEXPI pump 1, design, volume, flow rate have domain and range in DEXPI? This could give problems down the line if taken literally and used in machine validation in both DEXPI and IDO systems. That is a good question. I do not know. I have not found this, but maybe if Heiner is in the call and can answer that question.
Yes, here's Heiner, I'm in the call. Yes, in the moment we have the property definitions, let's say, only in DEXPI, and where we are waiting for is for the new property concept of ISO 15926 part 4. And that will be, I think, started next year. And then the whole world of properties, I think it's more semantic. Now it is only, let's say, human readable. What means design? Yes, that is a very important question. And there are answers, and perhaps in different domains there are different answers. And therefore, that is the reason why we have to do the whole property concept in part 4 again. Is that an answer for you?
Yes, thank you. There was also this direct use of the DEXPI property as a shortcut property. You maybe need more decoupling. But yes, thank you.
There is a question about that also, sort of more than 2 questions, or 2 comments.
Yeah, there's another comment by Mihaly, who is asking about this notion of design in the shortcut property and how this is sort of reflected in the ontology representation. To be honest, I didn't give it too much particular thought. I applied a modeling pattern that we use for shortcut properties. If design yeah, it opens a whole world of discussion now. One view, let's say, is that we need to separate the design document from an as-is representation or as-installed representation of the asset. And that leads to a discussion as to whether a design document should be the ontology, the IDO-based ontology itself, or the ontology representation of the asset, or whether the representation of the asset should itself be an information object. I think we need to discuss this further.
Yes, Dirk, that's important. And what we should know, design in this case as a property, we can have, let's say, the centrifugal pump as a non-individual existing physical object. Can have a property like design or a max design pressure. And the asset later on, the real physical thing, can have this property as well. And of course, the values, they must fit together. And that we have to clarify in, as I said, in the new property concept of part 4.
We are 2 minutes past the top of the hour and people are starting to leave or has left. So I think it's time to start. There is one comment we have, or one question we haven't answered. We will get back to that. So with that, we will also come back with what we are doing next, because we haven't made specific plans for the rest of the meetings we have this year. And that will be sent out pretty soon, I hope, and we will work on that almost immediately, but we need to get it in place. So with that, I would like to thank you so much for participating and hope to see you again in 1 week. Thank you.
Thank you.
Thank you. Bye-bye.
Thank you very much. Bye.